All right, good afternoon, everybody. I want to welcome you to the second lecture. I hope that your transition into the semester is going smooth so well. I have a set of directions up here for the in-class assignments. And as we go through, I'm going to reiterate what it is that I expect from you from each of those problems. But first, before I begin lecture, I would like to invite a fellow professor from our department, Nitesh Chawla. He is the head of the iTreads program, and he wants to discuss that with you really quickly and tell you what that's all about. So. All right, thank you, Ted. So I've also posted the website for that program as well as his email on the Slack. So does anybody, does everybody have Sakai up? Hey, awesome. Also, I have the Slack channel up on here. So if for those of you who might want to ask a question and maybe aren't as confident about projecting your voice or being able to hear, you can just type it in the Slack. I will monitor that through the course of the class. So the other announcement I need to do really quick before we start today is regarding the labs today. Two quick things. One, the labs have been moved to 228 DeBartolo. And two, there's still a need for 3 students in the 230 section to move because we had to move the room. There's an overflow and we have to make sure we're meeting social distancing requirements. So we'll figure all that out later. Okay, so what I'd like you to do is each lecture, we're gonna start out by doing a review problem or two, kind of get you to think about what we covered last lecture. And then what's gonna happen is after the time's up, I'm going to go over the solution with you, the benefit to the students. So please start doing problems 1 and 2 right now. And as I'm going to kind of give you a brief example of what the expectation is. So I'll describe to you the solution. The benefit to you is that you work through it and make an attempt. And then it gives you an opportunity to be honest with what it is you don't understand quite yet. And then you get an opportunity to review. And then tomorrow I'll post short videos that have the solutions to those as well. So please get started on that. Yeah, of course. Oh yeah, this is low risk, so you're welcome to refer to notes. This isn't like a quiz. Basically, the goal is make an attempt. If you don't know, that was your opportunity to go, okay, there's something I don't know, and you're doing exactly what I want you to. Refer to your notes. It's another opportunity to study and get some experience. Well, and as a little bit of a warning, because of the opening talk, I may have to cut 30 seconds off of the time I tell you here and there in order to make sure we get the whole lecture in. For those of you in the back, can you hear me better? Good, thank you. Thank you for pointing that out. Okay, so let's quickly go through these problems, and I'm going to tell you what the solutions are. All right, so the way that I would approach, there's going to be matching type questions on the exam. And so the way I would match it is to see the definition and try to match it back with the term. So An object shares a base set of properties with another object. Does anybody remember what that is? Yes, that is inheritance. Very good. All right, so hiding procedural complexity. Which one was that? Yes, abstraction. Very good. An inherited object has a different procedure. Which one is that? Yes, that is polymorphism. Very good. And that leaves D to be encapsulation, grouping, methods, and properties as objects. So now I'm going to scroll down to number 2, and let's match the definitions there. The server encountered an error. Okay. So an intermediate value in a register is placed back in the data memory. Does anybody remember what that is? I heard someone say it was store. That's absolutely right. So we store that in memory. So 5 is A. An area in memory that can be allocated and deallocated during the program execution time is the heap. This is really, there we go. C, memory for each function instances, including main and any function calls. That is the instruction stack. D, data is loaded from the data memory heap into the register. So that is load. And E, memory designed to be accessed to be written quickly and contain intermediate values. E is registers. All right, I'm sorry, normally I would ask everybody to try to provide answers, but I do want to make sure because of the beginning to keep on pace. Does anybody have any questions, or did anybody learn anything interesting from trying to attempt that problem? I'll quickly check the Slack and then we'll get going. Okay. So let me turn this up again. All right, for those of you back, I'm just getting another comment about the volume. Can you hear now? I'll try to make sure I project during the course of the lecture. Okay, so let me now go to the slides. All right, so the fundamental aspect of a data structure is a pointer. So we kind of broken this idea down where we have this computer architecture, and somehow I use these local fast registers to point somewhere on the data heap, and on that data heap we do some sort of structuring of data. So we're going to learn a lot about this today. And what you've demonstrated in your practice problems is that it's allocated dynamically, meaning that you use a function that you learned about in FunComp or intro called malloc, and you allocate the memory, and then you go through it based on the data type. So you can refer to large data structures in a compact way, and you can represent the relationship between those data. So when we get to things like trees, where in a node where it has pointers pointing to each element, we'll be able to traverse the data heap in order to find things efficiently. All right, so first, I'm going to show you this piece of code, and then throughout the course of the next 10 minutes or so, we're going to make sense of this piece by piece. And the more you understand this, the more you'll understand the lower levels of abstraction, and we're going to build up towards building our very first data structure. So what's going on here is I have an integer, and then I create an integer pointer with int star first pointer. In fact, I can even make it clear by bringing up this code here, int pointer. And then what's going on here is I set first pointer equals ampersand A. What that means is whenever I have an ampersand there, I'm asking for the address of A. So the pointer, first pointer, is containing the address of A. And then what we're going to do through the next several slides is describe what all this code is going on here. So first, what I want to show you is the 3 fundamental elements of a pointer. The first fundamental element of a pointer is that it's contained in a register and it has its own address. So that register is what we would call first pointer. That's its physical location in the computing device. Now what's going to happen, what you're going to see on the next slide, is that inside, the data inside that register location is going to be the address of another piece of data. In this case, it's going to be a piece of data on the data heap. And so what I'm going to do is I'm going to show you the next animation. And so inside there's an address, and then it points to a location. All it is a place. And we will call this a void pointer. A void pointer points only to a location. In a computer, when we get down to the nitty-gritty of memory, it's only zeros and ones. So you can point to a location, then you say, all right, I want the next one of those zeros, next 8 of those zeros and ones, and we'll interpret that as a character. There are 2 comments in the chat. Oh, this is lecture 02. All right, so the last part of the fundamental aspect of a pointer is the value inside that location itself. So the void pointer, what we're going to discuss in detail, is just the location. And if I want to say it's an integer, for example, the number 1, we're going to take the next 32 bits and interpret those zeros and ones as an integer. So that is how a very simple piece of integer data is structured on the data heap. Does that make sense so far? Let me quickly check the Slack. All right, who actually can hear me? Okay, so we're kind of getting mixed. We're hearing, I'm sorry, I have it about as loud as I can. I have to wear a mask, so let me. Is this better? Okay, good, good, good. Thank you. Sorry about that. All right, so now let's go over these 3 steps again and start relating them to what's physically going on in the machine. So a void pointer, the beginning, here we're going to call it the memory data register. It tells me where the memory begins, and it's in one of those fast registers. So to reiterate that point, I want to be able to do what's known as pointer arithmetic. This is why we had to go through the arithmetic logic unit. So what's going to happen is when I want to get a location, I'll say this is the base address of my structure of data. And then I'm going to perform pointer arithmetic to get to the specific location of the piece of data that I want. So what's going to happen is it's going to take the value, that MDR, memory data, that's the first part, the physical location, and then inside of it, it's going to contain the data's address, which I have here is data memory base address. And then that 0 means I want to get the data that's at the beginning of that data structure. Go to the very beginning. And then I'm going to perform an addition, and then that is the location of that specific value. So you get the base address, you're going to perform some pointer arithmetic, and we'll go into a lot more detail on that later today, and then you get to the specific location. Okay, does anybody have any questions about that before I continue? All right, so then this store is when I get to that location and take it back to a local register and perform some fast operations. I'm sorry, that's a load, my apologies. And that is what we call everything being dereferenced. I see a comment in the chat. What does the 0 represent? So I'm going to go through this in more detail, but it is what is known as the offset. And I'll show several examples of that today in lecture. All right, so one of the big things and one of the reasons why it's really important for you to understand what a void pointer is that computers do precisely what you want them to do, nothing more and nothing less. And as you build your own data structures, if you have a really strong understanding of how to convert a void pointer to a character pointer array, as we're going to do today, once you start doing that, go, okay, well, this is how I can then structure data with pointers to find things fast. Then you will build efficient, reliable data structures. When I say it's void, that's all it is. I'm pointing to a location, and it doesn't mean anything other than where it is. So that's what we mean by void pointer. So let's go over this again, except now we're going to add the concept of void. Now we're starting building closer and closer to what we want to do inside of the computer. So what's going on here is I have ampersand first pointer that refers to the address, as we've discussed before. When I do star first pointer, I want to get that location, and when I'm dereferencing the pointer, what I'm doing is I'm getting it from the data memory and loading it to the register. So again, I'm pointing to that location, and then star first pointer means I take the value 1, I copy it into a local register, and then I perform operations on it. Does that make sense so far? Okay. So now let's add void. Void star ampersand means in C++, we want to print the address. We're going to cast it. That's what the parentheses. We're going to cast void star, meaning that we're going to print out a physical address in the computer. When I have void star ampersand, what that means is I want the physical representation of the address of the register. When I take away the ampersand, remember that the register contains an address itself. So when I say void star first pointer, I want the physical representation of the address that it's pointing to. Does that make sense so far? So let me go through the animation to make it clear. So we have void star ampersand first pointer points to the address where our pointer is contained. I remove the ampersand, and that gives me the physical representation of the value itself. I'm sorry, the location it's pointing to. And then when I do star first pointer, that's dereferencing the pointer, which means we get the physical value. So that's a really important concept. So I want to make absolutely sure if anyone has any questions, please don't feel ashamed to ask. I'm happy to go over this over and over again until everybody understands. Yes? Absolutely right. So the question is, for those of you who might not have been able to hear, the question was, the void star without the ampersand means we're getting the location where we're trying to store the memory. Is that your question? So yeah, that's absolutely right what you were asking. So ampersand, void star ampersand means the address of the register. Void star first pointer means the place where we're pointing, and then star first pointer means we have dereferenced the data on the data heap. Let me check the Slack to see if there are any more questions. Okay, so now to go over the analogy one last time, I'm bringing in by picture the pupfessor as well as my wife, and we are going to go over the hungry pupfessor void pointers analogy, where void star ampersand is the physical location of the register. In this case, void star ampersand Erin is her physical location, right? It's her brain. So what's inside her brain right now? She's obsessed. Well, let me go through the animation. So right now, void star ampersand first pointer, that's Erin herself. What's going on inside her brain? She's hungry, she wants some food. That's void star first pointer. And then anything could be in my wife's hand, right? It could be cheese, it could be a snack, it could be a treat, it could be whatever Erin, like meat or something that Erin wants, right? So then we dereference what's there, and that is cheese. Okay, does that make sense to everybody? Okay, so what I would like to do is please take a couple of minutes to attempt problem 3 in Sakai, and then we'll go over the solution together. And just like the same thing, if you still don't understand, it's perfectly fine. Please feel free to ask questions. Okay, so what I'm going to do is I want to go over the solution to number 3 now. So which of the following are fundamental elements to consider with working with a pointer? So basically the concept I've been driving home. So the address contained in the program counter is not correct because that's just pointing to a location on the instruction stack. So the data within the pointer is the address of the data in the data memory, data heap, that is correct. The address of the register containing the pointer, that's the base element, that's Aaron's brain trying to figure out what if it's cheese, so that's C. And then the address of the register to store a dereferenced data, that's part of this load. That's not correct because that's not part of the pointer itself. And then the E, the information contained in the address and data memory, that's the location that's stored in the register. So it's B, C, and E. Does anybody have any questions or comments about that? Let's see. So Carlo asks, how is a void pointer functionally different from a regular pointer? So I'm going to go into this in a lot more detail, but the short answer is the void pointer points to a location only, and then we're going to start working on casting to types, which we will then interpret a set of number of pieces of bits of data to be able to interpret a data structure. All right, so and Matilda, I think that's the same question you had. So did that address your question? And if it did, please just say so in the Slack so that way I can continue on. All right, awesome. Okay, so now what I'm going to do is I'm going to break down this initial piece of code and relate it to everything I've been telling you so far. So first, I have void star ampersand first pointer. That's going to point to the physical location of the register. Then I say, give me void star first pointer. That's pointing to the location in data memory. When I say address of A, what you're going to notice, you see here that these two are the same. So the address of the integer A is stored in first pointer. So when I say void star first pointer, get me the value inside that register, and that value inside the register is the address of A. So that's why these two are the same. Does that make sense? Awesome. And then the last part is star first pointer gives us the value of 1. So when I run this code, if I say make int pointer, say, am I in the right lecture? No, I'm in the wrong lecture. My apologies. And we see that it does the same thing as we inspected. The difference here is that I also have star first pointer, which dereferences the value that we're pointing to, and I have A that's pointing there. Those two should give us the same result, and they do. Right, all of that code, by the way, that I'm going to show you, that's, if you go to that link, I have it all there, so you can go there and study afterwards. Right, does anybody have any questions about this so far? Okay, so I have a question. Can you explain again what the program counter is? Sure. Very quickly, the program counter is a register that contains the current instruction that we're operating on in the instruction stack. And when we start working with stacks, I'll go into more detail about that. Okay, so Emmy, please let me know if that addressed your question. All right, so this will actually provide more detail about pointers and arrays, and now how we move along an array to get a piece out of that array. So an array is a fundamental data structure where we start a specific location. If we have 5 integers, it's going to be 5 times 32 bits. I'm going to show you how we do that. So with a pointer, awesome, glad to hear it, Emmy. So remember, we go to this base address of the array, and it's the location, array base address. We then take the value out, and that goes to an arithmetic logic unit. And we say 0, that actually means the array address of 0. So 0, if it's an integer, it's 0 through 31. If it's a character, it's 0 through 7. That gives us 32 or 8 bits. We add that together and we get that location. And I'm going to show you how we dereference these bit by bit. But let's say I want the 5th element. So what this says here, and let me write it out so it's more clear. This says 5 times size of, and then in parentheses I have type. So if it's an integer, it would be 32 bits. If it's a character, it's 8 bits. And so what's going on there is where I want to start is 5 times 32 for an integer. That takes me to that bit, and then I get that bit in the next 31, and then I get that value. So if you've ever wondered why it is that we say that the initial value is array 0, this is because of the underlying pointer arithmetic. I want to go to the 0 location and then get those next values. Does that make sense so far? Any questions? And then that gets that specific location. So memory allocation. I'm going to walk you through various forms of malloc, and what this should do, and this should clarify some questions I saw on the Slack, is the difference between a void pointer and a character pointer. And most importantly, it's how the operating system interprets it. So here, what's going on is I have a function in C standard lib library that tells me to create a void pointer, go to that location, store something, and then whatever the size that I pass to it, store that many bits. And now we're going to reserve that for that specific data structure. Okay. So here I have an example, void int pointer, malloc 5 times size of long int. So a long unsigned integer is 64 bits. That is interpreted as 5 times 64, and that's how much memory is allocated on the data heap. And we use the void pointer to point to the base address so we can always keep track of where it is. All right, so on the next, yeah, okay, so my thought question is on the next slide. So in order to allocate memory, what you're going to see, and this is something we need to consider when we think about these production quality compilation rules, is that we have to pass a long unsigned integer to malloc. If you actually look at the definition in the C++ standard, it demands a long unsigned integer. Does anybody have an idea as to why it is that we have to pass a long unsigned integer to the memory allocation function? Yes, that's right. Your code might crash. Thank you, Step in Center Ceiling. Anybody, any educated guesses? There's no wrong guess. Yes. Very good. Unsigned because you can't have negative memory. It's not like you can put in a -15 and suddenly you'll just grow the amount of memory in your computer. So we have to put in unsigned. The long aspect is probably something that will help you get familiar with the difference between modern laptops and computers that were in the 50s. So computers, 50s, 70s, 80s, you know, it's exciting in 1986, you bring home a laptop that has 12.5 megabytes of memory. Like, wow, that's a lot. Nowadays, you have hundreds of gigabytes or even terabytes on a laptop. And the analogy that I like to live, so my cell phone somewhere, but this computing power that we use to get Apollo 11 to the moon is the same. You would need 5 of those to have 1 picture on an iPhone 10. So nowadays, we need to have a lot more consideration, and long unsigned int, the amount can go up to 2 to the 64. So that's significantly more than, so we can get to 18 quintillion as opposed to 4.3 billion. So that's why it's required. So what I would like you to do is take 2 minutes and attempt problem 4, please. And this should help you kind of get a little more familiar with void pointers and what's actually going on underneath the hood. Okay, who wants to tell me what they got for the answer? You can either raise your hand or I'll check on the Slack. One quick thing I'll say is there's only 2 days this semester where I have to judge you if you get a wrong answer the first time, and today is definitely not one of them. Yes. D, that's absolutely right. And the reason why, and so the D is just printing out 1B2 echo Charlie 20. And so what's going on there is that we've allocated a certain amount of memory, and then we ask with standard cout what's inside there. So because of that, we're just getting the value inside the register, which is the location that the point to, which is the base address. So absolutely right, the answer is D. Okay, so another crucial thing. So let me show you some code here. And I'm actually going to go over this in more detail. So this is void1.cpp, and it's not zooming. Okay, there we go, it's zoomed. So notice how I did malloc, and you see here at the end at line 23 that I call a function call free. What that is we're now thinking about this procedurally. I allocate memory, I do something with it, and then I free it. So nowadays, laptops, it's, with modern technology, there's a lot of things, there's a compiler area of research called garbage collection. You go through and you find all the memory that hasn't been cleaned up by the programmer. Back in the 80s and 90s, this was a real problem. They didn't have that, so that's why you would get a recommendation. They had to shut down your computer every 24 hours because the memory wasn't freed, and it would take up more and more and more of the memory. And as a result, there was less memory for the operating system to use, and it significantly slowed down the computer. So that's why I have this big spiel on the next slide about when you call malloc, you should always free the memory. So when I code, if I write a malloc line of code, I'll press enter several times, and then I'll do free and whatever I call the variable so that I always remember to actually free it. Does that make sense? All right, let me check the Slack. Why didn't you have it as print star void star hello? Okay, so that's a good question. In C, it's required because C is a purely procedural language, and in C++, the standard cout interprets it as an object and does the conversion for you. So that's another example of object-oriented programming and abstraction. But the reason why I'm doing it is because you're a C to C++ transfer in your coursework. So I'm starting out with the C and transitioning to C++. So Connor, did that address your question? Awesome. Okay, so what I want to do is I want to walk through this malloc code, and we're going to break it down using our knowledge of void pointers to see what's actually going on here. And then what we're going to do is we're going to translate that knowledge to bring it to what you're familiar with, which is array allocation. So you did a lot of that in C, and now once you see it, you're going to go, oh, that's what's going on here. So initially, you've got size of character. It's 8 bits or 1 byte. Then the next piece is 5 times. So now I have allocated 40 bits on the data heap. When I call malloc, I've allocated that, and I would put the address into a register, which we call void star VP1. Does that make sense to everybody? I'm happy to walk through it again if it doesn't. Okay. So now what we're going to do, and this is, and so Carlo, this is going to address the question that you asked. We're now going to try to transition from void star to a type pointer and what the difference is. And so here we have this, what looks really messy, but when I break it down to what this actually is, it will be very familiar to you. So I have this star parentheses. In front of VP1, I have char star +1. So let's break this down and make this make sense. Once this makes sense to you, you'll understand what's going on underneath the hood in arrays. So first, char star VP1. VP1 was initially a void pointer. However, the production quality compilation rules insist that if you're going to perform pointer arithmetic, you must indicate the type that you're going to add. So in this case, I have char star. And this is a security feature. If you think about it this way, let's say you have an array of 5 integers. And if you don't do that, let's say you just accidentally add 16 instead of 32 and then try to iterate through the rest of the array. What do you think would happen there if you're trying to read those values? Any ideas? Yes. Oh, no? Any guesses? So let me repeat that. We have an array, but instead of moving 32 from 0 to 1, I only move 16 bits, and then I try to get the next 32, the next 32, the next 32. What do you think would happen if I was trying to print those values out? You're absolutely right. You print out the wrong values. So what the security there is saying is, you got to tell me that you're moving 8 bits. So now, what's going on with this +1? Because C++ will treat this as objects, you cast it to a character and add 1. What the computing device will do with the C++ compiler is that will convert that to +8. So you say 2, that would be 16, so you'd go to 0, 1, and then 2. Does that make sense? So you're actually, now we're seeing some abstraction in object-oriented programming. Normally in C++, what you'd have to do is you'd have to say size of char, because you'd have to be explicit about it. But now we're starting to see a little bit of abstraction. The last part is now what? So now we're pointing to a specific location. And yes, question. Correct. So the difference is if this was just with char star VP1, we are telling the operating system that this piece of memory, which we initially allocated as a void pointer, all that memory, you need to divide that into 8-bit chunks, and they are characters. We are forcing that. It's explicit. Then when I say +1, move to the next chunk of memory. Did that address your question? Awesome. Any other questions? All right, so now let's do the last part. What we're going to do is we're now going to go to this. So now we have a specific location, and now we're breaking it down to the exact same thing. If you remember, we had first pointer. First pointer gave us a location on the data memory of an integer, and then we dereferenced it. So what we've done here is I have a location in the data memory, VP1, which I've allocated as a void pointer. Then I said, for safety, we have to interpret it as a character array. Then when I say +1, now I'm pointing to the next element. And then when I dereference it, what do you think I'm actually getting here? Yes. We are actually getting a character. It's absolutely right. So now we have done this. And if we had a character array, let's say char star VP1, this would be the same thing as VP1 of 1. You recognize that? I'm sure you've all done that in FunComp or intro. So that is what's actually going on underneath the hood when you use the array bracket operator. In fact, in the next slide, I have the animation that compares those. So let me clear that up so you can see. So now what I can do is this, when I dereference it, that's the equivalent of as if I had a character array and I got 0, or I got 0 and then 1. So 1 gives me those 8 bits. So Carlo, did that address your question more clearly? Awesome. Okay, oh, Carlo's sitting right in the front, sorry. All right, so now let's actually look at this. I'm going to go through the same thing, but now I want to show you what's actually going on on a block of memory. So here we have some data memory, and we have a bunch of characters. And so VP1 is a void pointer that contains the location on the data memory. So there's where it's pointing to, and to do that, we do char star VP1 for safety. So now I'm pointing at a location. So then when I say +1, what it's doing is it actually moves 8 bits. And then finally, when I dereference it, I get those 8 bits there, and I interpret it as a character. So here, this case, it turns out to actually be 111, which is lowercase o in ASCII. All right. Does anybody have any questions on that? All right, so now what I'd like you to do is I'd like you to attempt problem 5. And we're going to work through the difference just to clarify the difference between void star and what the actual values are. Bless you. Okay, so I see Sebastian. Okay, while you're working, Sebastian asks, why is char star before malloc necessary in char star hello? So that's in the problem. And what we are doing there is we are explicitly telling the operating system at the beginning when we allocate the memory that it is going to be in a character array. And then in order to go backwards, we'd have to actually cast to void star to get the address. That's why when you did it in C, you had to do it that way. Sebastian, did that address your question? Oh. Okay, so I'm going to show you what's actually going on with problem 5. So here we have a long unsigned integer, and we have char star hello. Now, if you remember from C, this is the reason why you had to put char star in front of malloc. So that way you are telling the operating system, this is always a character array. So now instead of void star, so now we're iterating through the length. So we have 5, and then here I get, say that it's hello. We iter, so it'd be 0, then 1, then 2. So we're actually moving that times the 8 bits. And then I have void star in front here. And so what I'm actually going to do is I'm going to have this initial location. So here I had, it was, the way to approach this on an exam is I would say C20. For a character, it would become, the next iteration becomes C21, C22, and it'll go all the way to C24. So C23 is in the middle there. So therefore, the answer is C. Does that make sense? Awesome. All right, so this void1.cpp, I showed this to you before. When I do it, it's going to allocate a certain amount of memory, and then it's just going to print out the address. So let me run make void1. And we see that it just prints out of address location. Does anybody have any question on that? Because what I'm going to do now is we're now going to move back and forth among different levels of abstraction. All right. So next, we have abstracting arrays. So here's what's going on here. We have char star VP1 doing the same thing. We have size of bits, 5 times 8 is 40. Malloc is allocating the memory. And then char star indicates the computing device to interpret the memory as a set of characters. And so this makes it a little easier to write the code. Procedural programming is you have the most control, but it's the hardest to program. So here we have VP1 plus 1. It's a little simpler. We don't have to cast VP1 because it's not a void pointer. So we already told the operating system that it's char star. So now we're treating it more like an object. We're a little higher level of abstraction. And what this allows us to do, it's a little simpler to program. VP1 is the base address, but we're interpreting it as a character. Plus 1 means that we are interpreting it as 8 bits. Then star, now it's starting to get closer and closer to what you're already familiar with. All right, so then the other thing, now we don't, I've said this before, we don't need to cast there in VP1 because we've already told the operating system, and now we're starting our process to move from imperative to object-oriented programming. So let me show you the next program, which is charl.cpp, that does the same thing as void star, but at a higher level of abstraction. So now I've cast this. In order to see the memory location, now I got to cast back to void star. So that should address, I think that was Connor's question. No, it's Sebastian's. So when I run make char1, it's going to do the same thing. It prints out an address. So on the next slide, I have a question. What do you think will happen if I were to remove the void star from in front of hello? So let me bring up that piece of code, and let's guess together. If I were to do this, if I were to say hello, and then update it, and then run make char1, does anybody have any guesses as to what will happen? Yes. I'm sorry, can you speak up? Oh, no, that's a good guess. It will compile. What's actually happening here in the code is that we've allocated memory, but we haven't told it what to do. The big thing with malloc is it puts everything at zeros. So what's going to happen is it's going to read through and say character value, ASCII value of 0, 0, 0, which is null. So it's just going to look like a big bunch of nothing. So when I run make char1, right here, it looks like it's printing nothing, but it's actually something. It's 8 nothings. So that's the important reason why it's important to understand at different levels of abstraction what's going on. But I really liked your guess. So let me fix that code so that way I can do the same demo in next semester's class. Next thing I want to discuss is new and delete. So for those of you who've coded in C++, you're probably already familiar with this. For those of you who haven't, the idea behind new and delete is to treat malloc and free as objects. The objective is to simplify and abstract the code. So what's going on here, if I'm doing malloc in C, the C++ version, I just say new char 10, and then when you compile it, it goes down to that procedural level and does that same amount of work. The objective of C++ accomplished the same thing, treating it as objects and try to make it cleaner. The next slide, I'll say this while you're all writing notes down. The next slide, I'm going to show you the difference between free and delete. When I did free, and then I called it, because it's a C function that does all this freeing of the memory underneath the hood. Delete, you just say delete, and the memory name, and it deletes everything for you. All right, so to address a quick question from Will McComas, let me move to the next slide so you can quickly take notes while I'm addressing this question. So void is nothing more than pointing to a location, but in order to interpret what that location contains, we then have to cast it to some sort of piece of information. What will become important as we go further into this course is that moving along the data heap and understanding what's going on will allow us to be able to make more efficient data structures. Well, did that address your question? Awesome. Okay, so now what I want to do is I want to show you array1.cpp. So array1.cpp has the same thing as void and char1.cpp, except now we're at the higher level of abstraction. Char star hello equals new char. Then I print out the address. I free the memory, but I could also call delete there, and it will work. So then if I do the same thing, make char1, it prints out an address. So now let's start actually traversing the heap here. So let me skip over that slide. So in void2.cpp, we're now going to iterate through and work on that problem, right? So what we did in the problem, and what you're able to think through correctly, is that this piece of code in void2 iterates through the entire memory and just prints the address locations. And you see that I have iter times size of int. That's one way of doing that. So if I do make void2, you'll see that it prints out those addresses. And I obviously did not update that from the last demo, from last year. So my question was going to be, what happens when I change it to int? So what's going on there is, when I change it to character, it outputs it in bytes. So you see how it says 1, 0, 1, 2, 3, 4, 5, all the way through F, or all the way through C. That's in, what happens here, if I'm doing this purely procedurally, is I can change that to int, and that updates it to, you see, 048C, because integers are 32 bits, so now it's going 4 bytes every time. If I do the same thing in char2, you see that I just changed this to iter. It's treating as an object. I don't need to cast hello because it's a char star, not a void pointer. And if I do make char2, it does the same thing. And if I go to the next level of abstraction in array2, we just see I say hello iter. It'll do, and I call delete hello here. You make char2, I'm sorry, make array2. And it does the exact same thing. So now we're seeing these different levels of abstraction. Okay, let me skip over this because you all have demonstrated you understand that. Char and array2. So now we're going to actually obtain pieces of information. So again, we go through, we cast character, and then we dereference to get the letter. And we can use char star plus size of char to actually get value. So here I have void 3. And what you're going to see is I have 2 pointers. Void star hello, where I've allocated memory, and void star reference. It's just pointing, it equals hello. That means it's another pointer that's pointing to the same location. The difference is reference does not have any memory allocated. So what's going on here is I have char star reference, and dereference is equal to 72, which is uppercase H. This line here, so I can zoom in, there we go. I'm performing arithmetic, and I'm moving the reference pointer to point 8 bits further. Does everybody see that? Then I can say that reference pointer is now I dereference reference pointer, and I say, now make it 101. And then what I'm going to do here is I'm going to print the address of hello. I'm going to print the value of hello and dereference it. And I'm going to do the same thing for reference, and we're going to see the difference. And then we can go over that code again. So we have make void 3. So hello is always pointing to H. I never move it. I perform pointer arithmetic on reference, and that moves one byte. And here, this is the actual location of the register reference. So we see that's a difference. We see that 0 and 1, that moves by 1. That's H and E. Right, let me skip over that for time. Now, char 3 does the same thing, except now I'm just doing reference equals reference plus 1. So these are char pointers. And so now it's a little higher level, but it will do the exact same thing. So I get the address, I just do void star hello, that's where it's pointing on the data heap. This ampersand hello points to the location of the register, and star hello and star reference are going to point to the values that it's pointing to. So then I have make char 3, and it prints the same thing. And so now what I want to do is we're now going to go to array 3, and array 3, we're now working at a different level of abstraction, where I've allocated memory using the new keyword. Char star is only pointing to one character, and then I dereference, put the value H there. I perform pointer arithmetic for reference, and it's E, and then I print out the same values here. So I'm now going to compile that and run it. And we did the same thing. At the level of 4, what I want to do is now I'm going to put all the values there. So we see here that now I'm performing pointer arithmetic to store all the values of hello world. And then what I do here is I'm iterating through, I'm printing out the address and the location, and as I iterate, I am moving the reference pointer. And so that allows me to use the hello pointer to keep track of where we're looking. So let me run make void 4. And now what we're doing is you can see that we're iterating through the data heap, and we have hello world there. I do the same thing in char 4, but now instead of having to do those numbers where I had ASCII values, I'm lifting it up to the next level of abstraction. I'm putting in the characters, and it's simpler to code. And then now I'm printing out the location of the reference and the character there. So I run make array 4, and again, it prints out hello world. And then if I do array 4, this is even simpler. Now I'm using the new keyword. I'm using my familiar array operators to be able to figure out what's going on. But underneath the hood, we have the same 2 pointers, hello and reference. And so then it iterates through, and then we see that I call delete. So I do make array 4. I'm sorry, I already ran array 4. Let me skip through all this. I apologize. We're going to skip problem 6. We only have 3 minutes left in lecture. But what I want to show you for the last 3 minutes is hello void, hello char, and hello array. So hello void, what I'm showing here in this slide, is this piece of code where I have long unsigned integer, num chars is 13. I create 2 void pointers, and I keep one hello to maintain the location, and then I iterate the other one. And it goes through and it's going to print out this character one by one. And then in this line here, it's going to perform the reference arithmetic. So when I run make hello void, it prints out hello world. When I move to the next level, hello char, we see that it's a little more simplified. Char star hello, I've allocated the memory. We did the same thing, hello. I go through and allocate those. And then we iterate through using the reference pointer so that way we don't lose track of where it is on the data heap. So I want to run make hello char, and we see that it also prints out hello world. Now hello array and hello array 2 and hello array 3, I'm going to break it down into higher and higher levels of abstraction. So here, char array, we're doing the same thing. We're now using those array operators. In hello array 2, I'm now just printing out, instead of using the pointer arithmetic, I'm just saying hello iter. And then at hello array 3, I'm doing char star hello world and printing it out. And we see that, oh, sorry about that. Hold on. And it works. So let me go to the last slide that I'll present today. So what's going on here on this slide is on the right, I have a very procedural, lowest level of abstraction in C, hello world, where I have to allocate the memory using void. Then I explicitly tell the operating system every single time to interpret as a character. And that's what's on the left. On the right, we have a very simple standard cout hello world program. At the beginning of the first lecture, I told you that what was actually going on was 2 pointers. And we see here on the right that that's what's going on. So the moral of this story is that if you understand why this works on the right, your right, my left, then you'll understand how to implement C++ at that object-oriented programming. I'll make sure to fix the problems. I apologize, I thought I'd have a little more time at the beginning of lecture. But on that note, submit it. It will say that you don't have all the points. I will fix that to make sure that everybody has the appropriate points. So on this last thing, just go to the bottom, submit. You also have until 11:59 tonight. So if you didn't understand something, you want to fix your answers, you're welcome to go to office hours and ask for help. So on that note, you are dismissed, and I will see you all either this evening or on Thursday.